A 1.5 liter mixture of H2, F2, and carbon monoxide has a total pressure of 700 torr at 280 Kelvin. If the partial pressure of F2 is 100 torr and the partial pressure of CO is 250 torr, what is the mass of hydrogen? For this problem, there's a couple of questions. We want to know the mass of hydrogen, so we need to know the number of moles of hydrogen. But to find the moles of hydrogen, we're going to need to know its pressure. Because remember, if you know the partial pressure of one of the gases, you can then figure out how many moles there are as long as you have the information like the volume and temperature, which it gives here. So we're going to start as a partial pressure question. We know the total pressure is equal to 700 torr. We know this is going to be equal to the pressure of fluorine, which is 100 torr, the pressure of carbon monoxide, which is 250 torr, plus the pressure of hydrogen, which we don't know. That H is a little big, it should be smaller, but that's okay. So 700 minus 100 minus 250, we get that the pressure of hydrogen, now with the small h like it should be, is equal to 350 torr. Now this unit isn't going to help us, so we're going to need to convert it to atmospheres. That way we can use our PV equals in our T equation to solve for N. So if I have a pressure of 350 torr, I know that for every 760 torr, there's 1 atmosphere. So we're going to get 350 divided by 760. We have a pressure, make sure, yeah, that's wrong, of 0.461 atmospheres. And from here, we can now solve our equation. Remember that this is just a rearrangement of PV equals nRT. We have N equals PV over RT, because we want to know N. Remember, we want to specifically know it for hydrogen, so I'm going to have NH2, pH2. Remember the volume, it doesn't matter. It's the same no matter which gases they are because the container is the same. And the temperature is the same too for all the gases. So those, it doesn't change depending on what it is. But the pressure does. So we have 0.461 atmospheres times a volume of 1.50 liters. We then have an R of 0.0821 liters times atmospheres over moles times Kelvin. We then have a temperature of 280 Kelvin. From there we can find our moles of N2. 0.461 times 1.5 divided by 0.0821 divided by 280. So from here, we're going to get that we have 0.0301 moles of H2. So now, the problem wanted to know mass, not moles. So we have 0.0301 moles of H2. We're going to convert that because we know that for every 1 mole of H2, there will be 2.02 grams. So multiply 0.0301 times 2.02. We are going to get that this is 0.0608 grams, or 60.8 milligrams, if it were a multiple choice and you had to answer in milligrams. Gases are pretty light, so that's reasonable. Okay, so that's our second question. We found the mass of hydrogen, even though initially we didn't know the pressure even. We had to find that first. So that's a way we can use our partial pressure question first and then do something else with it later, like the PV equals nRT and then converting it to moles, or to grams from moles. So just you have to pay attention to what information do you have? What equations can you use to get towards that? Because a lot of these questions will have you use 2 or 3. No individual one is too bad, but it's just making sure you pay attention to, oh, okay, that's what I need to do with that. So let's try the last one now on the partial pressures questions page. We have a 10-liter tank of gas containing 30 grams of nitrogen, 125 grams of oxygen at 300 Kelvin. If the temperature does not increase, what is the pressure if 20 grams of CO2 is added to the gas mixture? Okay, so in this one, we're told the temperature doesn't change, so we have 300 Kelvin, and we've got a 10-liter tank. There's no reason to think, we don't have anything that tells us that's going to increase or decrease. So the only thing that's going to change is the pressure then. So we know N and T, or we know V and T, and we can find N. Then we can find P. So we already know our volume is 10 liters, and our temperature is 300 Kelvin, and the problem tells us the temperature does not increase. So I need to find is how many moles of gas I have. So in this case, we tell you add 20 grams of CO2. It's just saying it's part of the mixture. So we have to take each of these 3, find out how many moles there are of each. So we're going to start with our 30.0 grams of nitrogen. Because remember, we can add our moles together to get our total pressure, like we did on the part one video. If you don't ask for partial pressures, because this doesn't ask for the pressure of each, you'll be able to just add all the moles together to find the pressure. We know that for every 28.02 grams of nitrogen, there's 1 mole. So this is about a mole. So 30 divided by 28.02 is going to be, this mixture has 1.07 moles of N2. So we have 125 grams of oxygen. We know that for every 32 grams of O2, there's 1 mole. So 125 divided by 32. This is going to give us that we have 3.91 moles of oxygen. And then finally, we added 20 grams of CO2. So we know 12.01 plus 30, that for every 44.01 grams of CO2, there's 1 mole. So this isn't even a whole gram. This isn't a whole mole even. So this is going to be 0.454 moles CO2. So if we want moles total, it's just going to be these three added together. So 1.07 plus 3.91 plus 0.454. We are going to get that we have 5.43 moles total. And that's just from adding these three numbers that I underlined together. So now we know the moles, we know the volume, we know the temperature, we can find the pressure. So pressure equals nRT over V, just a rearrangement of PV equals nRT. So we have 5.43 moles. We have an R of 0.0821 liters times atmospheres over moles times Kelvin. We then have a temperature of 300 Kelvin, which it tells us doesn't change, so it's still a temperature. And then we have a volume, 10.0 liters. So 5.43 times 0.0821 times 300 divided by 10. So we're going to have a pressure of 13.4 atmospheres. Oh, if I made it 4 sig figs, it could have been 13.37. Okay, so I'm just going to write that, and this is one of those things where I write kind of big when I'm putting this on the screen. 13.4 atmospheres. That's our pressure. Make sure to write your units. It's not just 13.4, it's 13.4 atmospheres. So you don't write units, you could mean torr or bar or some other thing. So that's our 3 partial pressure questions. Well, 2 on this PowerPoint, 1 on the YouTube, and 1 on the previous. So now let's look at a stoichiometry question. Let me check something real quick. Okay, yeah, this is the last slide. So for both of these questions, we're going to use the chemical equation CH4 plus oxygen gas goes to CO2 gas plus 2 water liquid. So for this one, we will notice that it's already balanced for us if we check. Well, no, is it? Yes, because you have 4 hydrogens on both sides. You have you've got 4 oxygens. We're not quite balanced actually. So let's do that first. So I have CH4 plus, let's see, so 2 oxygens, O2s, is going to go to CO2 plus 2 H2O. So that wasn't quite balanced yet, right? Because we've got to take into account the fact that there are now 4 oxygens on the right, 4 on the left. There's 4 hydrogens on the left, 4 on the right. There's 1 carbon on each side. So now we're good. So the first question was, what volume of methane gas, assuming excess oxygen, is needed to synthesize 10 grams of water if the system is at a temperature of 315 Kelvin and a pressure of 1.05 atmospheres? So we're going to start with our starting information. We want to make 10 grams of water. And we're going to so we need to know how many moles, or else we can't use our chemical equation. So we know that the 18.02 grams of water has 1 mole of water. And the problem asks us, it wants to know how much methane we're going to need. And so if we look at our chemical equation, we know that for every 2 moles of water, we're going to need 1 mole of methane. So that, 10 divided by 18.02 divided by 2, we're going to need a total of 0.277 moles of methane. So now it asks us what volume is needed. So we've got our moles, it tells you the temperature and pressure are going to be constant at 315 and 1.05. So we just need to find volume. So V equals nRT over P. So we're going to have 0.277 moles. Our R is going to be 0.0821 liters times atmospheres over moles times Kelvin. We then have a temperature of 315 Kelvin. And we've got a pressure of 1.05 atmospheres. So this is going to tell us how much volume we need to have for it. 0.277 times 0.0821 times 315 divided by 1.05. So from there we get that we would need to add 6.82 liters of methane. That's how much we're going to need to add to be able to make our 10 grams of water. Because since we have excess oxygen, we didn't have to worry about that. Okay, so that's our first question. And that was we're just using a chemical equation as part of this. So now I'm going to, best I can, get this stuff erased because I want to keep the chemical equation up top. So, it'll take it a second. So, when we have a mass of water, what mass of water could be produced if we have methane and oxygen are mixed together in a 1.5 liter container at 30 degrees Celsius? If the partial pressure of methane was 0.5 atmospheres, the partial pressure of oxygen was 1.5 atmospheres. Okay, so the trick now is we've got a question that's going to be a limiting reactant question. We have to worry. Also, I'm actually going to make some more room. What I'm going to do is I'm going to erase this question for now, the one we're not doing, so there's more room. So we've got a limiting reactant problem. We've got to figure out how many moles we have of each compound and see which is going to tell us how much water we can make. So we know the volume and the temperature, although we've got to get it in Kelvin, and we know the partial pressures, so we can find the moles of each. So first I'm going to find my temperature is equal to 30.0 plus 273. It's going to be equal to 303 Kelvin. Okay, so let's find each of these. So first I'll do in my moles of CH4, which is going to be equal to our pressure of CH4 times our volume, which is the same for both, over RT. So this is going to be equal to pressure is 0.50 atmospheres. Our volume is going to be 1.5 liters. Divide this by our R, 0.0821 liters times atmospheres over moles times Kelvin. Our temperature is going to be 303 Kelvin, which we just found. So multiply all these together, 0.5 times 1.5, divided by 0.0821, divided by 303. From here, we are going to get 0.0301 moles of CH4. So now we need to find our moles of oxygen. We have NO2 is equal to, just like above, pressure of O2, volume over RT. The pressure of O2 is 1.50 atmospheres. We've got a volume of 1.50 liters. We have an R, 0.0821 liters times atmospheres over moles times Kelvin. We have a temperature, it's still 303 Kelvin. So we are going to have 1.5 times 1.5 divided by 0.0821 divided by 303 Kelvin. So we have 0.0904 moles of oxygen. So the issue now is we've got to figure out which is our limiting reagent. So we're going to convert this. We know that for every 1 mole of methane, we can make 2 moles of water. So we would get that our 0.0301 moles of methane times 2 is going to give us 0.0602 moles of water. Our 0.0904 moles of oxygen, we know for every 2 moles of oxygen, we can make 2 moles of water. So we know we can make 0.0904 moles of oxygen. So as you notice, Our methane is our limiting reagent, so we're going to make 0.0602 moles of water. And to finish up the question, we know that for every 1 mole of water, there are going to be 18.02 grams. So 0.0602 times 18.02. We are going to get, I'm just going to write above because I ran out of room right at the side, 1.08 grams of water can be made. So you notice this question, while there's a number of steps to it, a lot of it's stuff we've done before. So the first half was just do a PV equals nRT problem. Find how many moles of both gases. So that by itself is something we've done in our partial pressure section. Then the second half was, now you have a limiting reactant problem. Do the stuff from, is that second exam or third exam? Third exam. Do the stuff from the third exam with limiting reactants. And we just have to combine the two steps together. The trick that holds it all together is the moles. You'll notice we do this a lot with these things, right? As we find once we get to moles, then we can do some stuff with it. Okay, so that'll cover everything for the gases chapter. Remember to still go back and check out the concepts as well. Look over my slides, use the book if you'd like to be able to help out with that, to make sure you have an idea of what all the terms are, in addition to being able to do all this math stuff. Because sometimes the math problems require you to have some concepts. We also have a lot of questions that are just about, so what do we know about the concepts? Not just, how do I do some math with them, but what do the numbers actually mean? I wish you the best of luck, and I will get the Chapter 10 video out as soon as I can.